Hello students, good evening everyone. Yes, welcome to the physics session guys. Welcome to the physics session. Are you getting my voice clearly? Just drop me a message guys. Drop me a message. Are you getting the board clearly? Is the board visible clearly? I think some colors due to the contrast um, it looks like they're different. Okay, so okay guys. Yes, no, no. Okay, thank you, guys. Thank you, Rishwant, Shubha, Dinkaran. Once again, guys. Yeah. So let's go through this briefly. A couple of minutes. Telescopes part. Let us revise this. Let me revise briefly. Yeah, telescopes. Then I'll give you the brief explanation about the last remaining concept called reflecting telescopes. Then we'll go ahead with a few more numericals. So inform to your friends to join quickly, as this part we are not going to again revise in the tomorrow session. We are not going to revise. Inform to all of your friends, guys. Right. Just let me drop a message also. Okay, guys. Yeah, fine. Yes. Once again, let us revise this briefly about the telescopes. Telescope. Telescope. Telescope is nothing but an optical instrument. Yep. Telescope is nothing but an optical instrument which is used to view distant objects like stars, planets, heavenly objects like this, and also galaxies, and even not only those very distant objects like this kind of heavenly objects, very distant mountains to see, very distant mountains and buildings also you can see by using telescope. Okay, so telescope is an optical instrument which is used to view distant objects, which is used to see distant objects clearly. These telescopes are broadly classified into two types. They are classified into two types: refracting telescopes and reflecting telescopes. And actually, there exist too many different types of telescopes are there. This is briefly about the broad classification of telescopes, which we are going to have an idea, brief idea. There are so many things are there. A telescope is a vast and a very big concept. So we are not going into the details of so much. We are not going to the not that much detailed discussion. We are not going. Brief idea and important stuff, whatever is required in our level, we are going to discuss now in NEET and JE level. In NEET and JE level, okay, right? So telescopes are broadly classified into two types: refracting telescopes and reflecting telescopes. Refracting telescopes, again, we come across so many different types of refracting telescopes: astronomical telescope, terrestrial telescope, Galilean telescope, right? And in reflecting telescopes, again, normal reflecting telescope, we come across two kinds of actually there are so many different types of there, but we are not going to discuss many different types. Usually here we discuss little briefly about one of the type called Cassegrain reflecting telescope. Cassegrain telescope, reflecting telescope, and this only we'll discuss here. And there are a few more other types are there, like a Newtonian telescope also, which also come under reflection telescope, and some other kinds of telescopes also there. We will discuss briefly about only Cassegrain telescope here. Okay, right. Now let us see first refracting telescopes. Briefly about refracting telescopes. Before going ahead with the refracting telescopes, we need to have an idea about magnification power. What is magnification power or magnifying power of a telescope? Magnification power of a telescope, of a telescope. Okay, so magnification power or magnifying power of a telescope, M, denoted by M, is defined as the ratio between visual angle formed by the final image at the eye and visual angle formed by the object at the eye. Or you can say simply M is equal to visual angle formed by the final image by visual angle formed by the object. They are represented by theta and theta naught. So simply we can say M is equal to theta by theta naught. This is very important formula, guys. Remember this. Then now we'll see with the help of this what is refracting telescope. Briefly, its ray diagram, and and how to find the magnifying power for this refracting telescopes in different cases. Refracting telescope. Refracting telescope is given by this. So it will have two two converging lenses, means convex lenses of different focal lengths. If you recollect back microscope, one of the microscope called compound microscope. In compound microscope, we will have an objective of a smaller focal length and eyepiece of eyepiece of larger focal length. Okay, but here in reverse, there we have this was objective, this was eyepiece, but here in reverse, objective will be what do you call a convex lens of larger focal length and larger aperture, and eyepiece will be smaller. The eyepiece will be having smaller focal length and hence smaller aperture. So this combination we will use to see distant objects, because telescopes are used to see distant objects. And why we are using this is, if when you are using this to see a distant object, we need to collect more light so that the image can be having more clarity. For that purpose, we use what do you call an objective of larger focal length and hence and larger aperture, so that it can collect more and more light and it gives an image, a clear image. For that purpose, we use this. Okay, now if you observe a light from a distant object, means at infinity, if you are looking into a star, usually it can be considered as at infinity, and we know that light rays from infinity will be considered as parallel rays, actual rays are parallel rays. So if these two, if you consider parallel rays, if this parallel ray is passing through optic center, it passes undeviated, and another one which if it comes here and after refraction it bends and comes here and meets at this point. This point of meeting will be called as focus. If the object is at infinity, image is said to be formed at focus. Focus of this called as objective. So we can say the image distance for the object will be equal to focal length of the objective lens. So here image will form. This image will act as the object for the objective lens. So we will consider this as object distance UE. For this is eyepiece, right? Object distance for eyepiece. And for this will form a final image. So to understand that, if you consider a parallel ray and a ray passing through its optic center, it passes undeviated, but this will refract and passes in such a way that if you here for this, if you consider usually just here in diagram it may look like it far away, but usually you have to construct this lens somewhere here nearby. Okay, so if it is within the focus of this, then this image will be forming at a far point, or I can say even at infinity also. But the image will be erect and magnified, highly magnified. And this image can be, formation of this image can be understood by extending this size like this, and image of the object can be expressed as A dash B dash, and that of the eyepiece can be expressed as A double dash B double dash. Now, the angle made by this ray from the object, that is, you can say that angle made by the object at the eye, or here in this lens, you can take it as a theta naught. Whereas angle made by the image, final image at the eye, at this eyepiece, the corresponding eyepiece will be taken as theta. The ratio of these two angles will give us magnification. So in general, from the figure, you can say tan theta naught, this one, tan theta naught, here this is theta naught, and this is this height of the image for object 2, this will act as height of the object for this one. So if you take this as h, then if you take tan theta naught for smaller angles, it is approximately equal to theta naught, it is equal to minus h by, this distance will be f naught, minus h by sign convention, the heights below the principal axis will be negative, above will be positive, and here the f naught is, we are measuring in the direction, so it will be positive, so it will be minus h by f naught will get with sign convention if you consider. And tan theta is equal to again opposite side by adjacent side, here opposite side is h, adjacent side is ue, so we can take it as theta equal to h by ue. And if you substitute this in magnification formula, you will get magnification of a telescope, or magnifying power of a telescope is given by theta naught equal to minus f naught by ue. This is the general formula for magnifying power of a telescope. Okay? What telescope? Refracting telescope. But if you consider here two special cases, like if the final image is forming at infinity or at relaxed position, for the eyepiece, image distance will be taken as infinity. For the eyepiece, image distance will be taken as infinity. And object distance will be minus ue by sign convention, and its focal length will be of course positive fe. Then by substituting these parameters in lens equation, we get 1 by fe is equal to 1 by ue, or 1 by ue will be taken as 1 by fe. So we got the different expression for magnifying power of the refracting telescope. For the final image to be formed at infinity, it is represented as m infinity is equal to minus f naught by ue equal to minus f naught by fe, because 1 by ue is 1 by fe. And this is also called as relaxed position magnification. When 1 by ue is 1 by fe, ue will be equal to fe. Here the distance between the objective and the eyepiece will be called as tube length or telescope length. It is represented as v naught plus ue, as v naught is f naught plus ue. In this case ue is fe, so you can write it as f naught plus fe. So in this case L infinity becomes f naught plus fe. We may need this also while doing some numericals. Remember this. Next, if final image is forming at least distance of distinct vision or for strained position of the eye, then magnification, if you want to find, as magnification is f naught by fe, f naught by ue. Here, when v is minus d, and ue is minus ue, 1 by fe is equal to minus 1 by d plus minus of minus becomes plus 1 by ue. Here from this 1 by ue is 1 by fe plus 1 by d. This you have to remember, guys. This relation you have to remember while doing numericals also. Sometimes we use this formula directly. Okay, so this on simplifying you can write d plus fe by fe into d. This on substituting here in general magnification formula, that is f naught by ue. So 1 by ue is this, so you can write this one, and on simplification is further by taking fe here, you can write minus f naught by fe into d by d is 1 plus fe by d. This is the expression for magnifying power of a telescope when final image is forming at least distance of distinct vision or at strained position. So correspondingly, the tube length or telescope length is given by f naught plus ue, where ue 1 by ue is this. So ue is reciprocal of that. So if you substitute this, you'll get this one. By using this, we have worked out some numericals. I think you remember those numericals. Now let us go ahead with the next. This is briefly about refracting telescope and magnifications. Now let us see briefly, based on this, some numericals we have discussed already. Few more numericals now we will discuss once again after discussing the concept of reflecting telescopes. Now write down subheading. So now I am removing this green page. I would like to bring back the white page, guys. I would like to bring back the white page, whiteboard page color. I want to say, I want to change. Yeah, right. So reflecting telescope. Now write down the subheading. Reflecting telescope. Reflecting. Write down by use this only. This reflecting reflecting telescope. Reflecting telescope. So obviously in refracting telescope, uh, one second. Before going ahead with the reflecting telescope, a few more points I would like to give here. In the ray diagram, if you observe in the ray diagram, where is the ray diagram? Oh, this is the ray diagram. Oh, this was in white color. So I hope nothing is visible, maybe in the screen. Let me briefly again give you this. This is the objective lens, and this is the eyepiece. Okay, if light ray passes through the optic center here, it passes undeviated, optic center of the first one, and it passes undeviated. So the angle made by this with principal axis, we can consider this is the principal axis. This will be theta naught. It is, of course, it is clear now. And the light ray passing parallel to this, after refraction it will bend. It will, I have to just understand this will bend and passes through, it meets at this point called focus. This gives you the image, first image, you can say, you can call it as a dash, b dash, and this will act as an object for this eyepiece. So to understand the final image, this passes undeviated, and this will bend and passes, so that they will never meet. So if extend this, you will get the final image somewhere here, I double dash or a double dash and b double dash. So b double dash, this is taken as final image, and this is observed to be making a subtending an angle theta here. So then all these parameters you have to remember. This is f naught or v naught. V naught is equal to f naught, and this is u naught, and this is l, and this is l. Right, now let us go ahead with few additional points here. So we have discussed the different types of refracting telescopes. Refracting telescopes. Refracting telescopes. Here, one is astronomical telescope, and next is terrestrial telescope. Another one is Galilean telescope. In astronomical and terrestrial telescopes, astronomical telescope is used for viewing heavenly objects like stars, planets, etc. But these, yes, Nana, Nafis, do you want to say something? If you want to say something, just you can give me a call also. You can give me a call as well if you want to say something, or you can send a message in the chat box itself. Okay. Otherwise, just if you are wishing me hi, yes, hi, just go through this one. Go through. Astronomical telescope and terrestrial telescopes uses two convex lenses only, whereas Galilean telescope will use objective lens as convex lens, but eye lens will be as a concave lens. That's what I would like to make a note here. So before going ahead with before going ahead with this, make a note of it. Try to keep a note. Okay, first point. What is that? Astronomical telescope, astronomical and terrestrial telescopes, and terrestrial telescopes telescopes will use convex lenses, convex or converging lenses as as objective and eyepiece O and E, whereas Galilean telescope Galilean telescope use or uses Galilean telescope use convex lens as convex lens as objective, and concave lens as eyepiece. You have to remember this. So concave lens focal length will be negative. So while doing the numericals, you have to remember that relation whenever you come across Galilean telescope. That's it, guys. Nothing else is there. Okay, that's it. Next. So now let us try to write down a subheading. What is that? A reflecting telescope. Reflecting telescope. Reflecting telescope. So obviously, refracting telescope will have lenses, either concave or convex. But we have understood that just briefly. What is that? Astronomical and terrestrial will consist of convex lenses, whereas Galilean telescope will consist of convex and concave combination. Here, reflecting telescope, obviously it has to use a reflecting element. Here, the reflecting element should be nothing but a mirror. So how this construction will looks like, and how the ray diagram looks like, let us see the ray diagram of reflecting telescope. And specifically we will discuss about one of the reflecting telescope called Cassegrain telescope. What is that? Cassegrain telescope. Cassegrain telescope. Cassegrain telescope. So it consists of two mirrors, one concave mirror and another convex mirror. How they will be arranged? Let us try to understand briefly. It will consist of a concave mirror split in this form, a concave mirror split in this form. Okay, here this is silvered on outer surface, and this will be arranged in such a way that it is arranged in a tube, so that let me draw a little bigger one. Okay, yeah, okay, this outer side is silver, and it is connected to a tube, so that at this point a convex lens will be arranged. And how it behaves and why it is used, you will understand while just in a minute, in few seconds. Here one more, here you can consider an axis passing through the center, you can consider principal axis or whatever it is. With the common axis, we consider one more mirror here, a much small mirror having a smaller focal length, but this will be silvered inside, so that reflection takes place on outer surface. So it is a convex mirror, this is a concave mirror, this is a concave mirror, this is a convex mirror. Okay, so this is supposed to be having a focal length f here. Okay, focal length f here. Actually, why we need this also, just we need to have a brief idea about these telescopes which are using lenses will create or will produces some aberrations, errors called aberrations, like spherical aberration, chromatic aberration, and some addition, like some kind of errors. We call them as aberrations. To overcome those aberrations, we use mirrors, but mirrors will be having a least value of aberrations comparing with the lenses. Comparing with the lenses, mirrors also will possess those, but they will have least value of those aberrations, chromatic or spherical aberrations. What are those chromatic and spherical? Let me I'll give you briefly, just for understanding purpose. So if you are having a lens, and if light is passing, and if it is having different colors, okay, different wavelengths, okay, different colors belongs to different wavelengths, and lens, the different wavelengths experiences different refractive indices when it is passing. Okay, so they will focus at different points, so they will give images at even though you have a point object also, it will give excellent image. So so the image will look like blurred, you will not get, you cannot see clear image. So this kind of aberration can be called as chromatic due to color variation. Spherical aberration is again the same, uh, you can say that the same light, if you are passing, if you are incidenting here, because of the thickness, so here you can say the rays which are closer to the principal axis and away from principal axis, closer to the principal axis are called as paraxial rays, and whereas the rays away from the principal axis are called as marginal rays. These rays will be focused at somewhere, and these rays will be focused at somewhere, so because of that the object image will not be sharp image, it will be kind of a blurred image you will get. So this kind of errors can be rectified when you use mirrors. So you can say simply here as a note also, afterwards you can write to this will be used for rectifying the spherical and what you call chromatic aberrations. We will use this. So this is the construction of Cassegrain telescope. In this, if light rays from the distant object, from the infinite object, if you consider them as parallel rays, if parallel rays incident on this, if parallel rays incident on this, this will reflect, this will reflect, and so this will have common focus. Maybe if this focal point is this, for this also focal point is this, it's supposed to go and focus somewhere here. Just briefly I'm giving you, okay, and this also reflects and pass, try to reflect and incident on this surface of the what is this called as convex mirror. When the light falls on this convex mirror, this further reflects, this further reflects and try to passes through this, passes through this, and as a result here if you observe, when if they meet at this point called, if it is the focus of this, if the light rays from the focus they are incidenting on this, they will passes parallelly, and the what do you call image of the object which is at infinity will be forming here. Okay, this image will be observed with the eye, this image will be observed with the eye, so clear image without aberrations. So this is the brief construction of the what is that ray diagram of Cassegrain telescope. And here the, for this also, magnification of or magnifying power of this Cassegrain telescope is also expressed as, is also expressed as f naught by fe. I can say that f naught by ue, f naught by ue, f naught by ue. But here also under two special cases, that is for the final image to be formed at relaxed position and at infinity. Okay, here the infinity means there will be parallel rays at what you call least distance of distinct vision. So but we are not going to discuss this in detail, the derivations part. So final image at strained position, if they forms, then corresponding magnifications are given by f naught by fe, and here f naught by fe into 1 plus fe by d. Same formula are applicable for this also. Okay, right, this is briefly about what you call Cassegrain telescope. And Newtonian telescope is another, is one of the another telescope which come under reflecting telescope, where this that is not there in portion, so no need to worry about that. So try to remember this briefly, try to copy this and have an idea about these relations also. While coming across the numericals based on this, you can work out. Now let us try to work out few numericals based on these telescopes. Specifically, you will get usually if you observe the previous years in different competitive exams, usually you will be getting the questions based on uh, what you call refracting telescopes. Okay, so but the formula related to this also same, so we will use this mathematical relations only. If you come across the questions based on this, we can use these relations. Right, now let us try to work out few more numericals, guys, from level 2 exercise 2. From level 2 exercise 2, level 2 exercise 2, level 2 exercise 2. Right, so I think already I have got a few questions. Now let us see this question. Question number 79. Let us see question number 79. Question number 79. Page number 183. So let me read the question first. Let me read the question and I'll listen and understand what is given and what you are asked to find. It is given that four lenses of focal length 15 centimeter, four lenses of focal length f1 is equal to 15 centimeter and f2 is equal to 20 centimeter and f3 is equal to 150 centimeters and f4 is equal to 250 centimeters. So four lenses of focal length 15, 20, 150 and 250 centimeters are available for making an astronomical telescope. Full stop. To produce the largest magnification, the focal length of the eyepiece should be. How to find that? Here, no need to do any calculations. So you have to understand this by looking into the formula of magnifying power. So we know that magnifying power is given by for what you call for the image to be formed in infinity or in relaxed position, m infinity is equal to f naught by fe. So for magnification to get largest magnification, the question you have to observe carefully. To produce the largest magnification, focal length of eyepiece should be. To produce largest magnification, you have to select the lenses, objective and eyepiece lenses, so that focal length of object should be. We have to better write down this as a note. For largest magnification. Okay, focal lengths of focal lengths of objective and eyepiece or eye lens. Objective and eyepiece should be objective and eyepiece should be objective focal length should be larger, so the total value will be larger. To get this maximum value, denominator should be least possible. So focal length of objective and eyepiece should be a maximum and minimum possible values. Dinakaran, sir, Cassegrain telescope, explain once again. Yes, so, yes, Nana, just a minute. Just after finishing this, I will explain once again. Okay, should be minimum for maximum and minimum possible. So, focal length of object should be maximum possible, and of eyepiece should be minimum possible. Out of this, if you want to use the focal length, you can use for maximum magnification. You can use this focal length f4 as objective focal length, and least focal length in this out of this is f1. So this we have to use as eyepiece, then only you will get maximum or largest magnification. So out of the given four lenses of focal length which you can use as eyepiece, the one which is having the least value of focal length, the one that is nothing but f1. So your answer should be what is that? 15 centimeters. So answer should be Fe should be equal to plus 15 centimeters. That's it. Okay, right. So let us see once again what is this Cassegrain telescope ray diagram. Hmm? Cassegrain telescope. So as I told, there are two types of telescopes, refracting and reflecting. In refracting telescopes, we will use lenses. We will use lenses. In lenses, usually we get here. If you want this, you can write down as a note. As a note, write down. In refracting telescopes, in refracting telescopes, lenses produce refracting lenses produce aberrations, errors or aberrations. In refracting telescopes, lenses, whether it is convex lens or concave lens, lenses produce aberrations, aberrations like spherical aberration, spherical aberration and chromatic aberration, chromatic aberration, etc. To avoid this or to eliminate this or to reduce, you may not completely eliminate, you can reduce it. To reduce these aberrations, we use the reflecting telescopes. Okay, so main use of reflecting telescopes is to reduce what? The aberrations, spherical and chromatic kind of aberrations. We use the reflecting telescopes. So you can say here, and also there are so many things out there. While to construct this, we may need to spend lot of okay, you can say we have to spend a lot of manpower and cost and etc. So with this, but whereas in this, no need of spending those things. So here you can say that to avoid this, specifically to overcome this, we use this. So Cassegrain telescope consists of two mirrors. This is called concave mirror, concave mirror, and this is called convex mirror, convex mirror. Okay, when light from a distant object comes, when light from distant object comes, we consider it as a parallel ray. This parallel rays on incidenting on this mirror called concave mirror, it reflects according to the laws of reflection. At this point, if you draw a normal, it reflects symmetrically, so that it reflects and it reflects and it falls on the another mirror arranged here. This another mirror having smaller focal length, called as it is a convex mirror. So inside is silvered, outside is allowed for reflection. This kind of mirror is called convex mirror. Okay, it falls on convex mirror. Again here, if you draw a normal here, about this normal, it reflects symmetrically and it tries to focus here. And similarly, this parallel ray on reflection from this incident on the this smaller mirror, a convex mirror, smaller convex mirror, and reflects, and these two will focus over here. After focusing, they will passes through, and as it passes through and incident on a lens arranged in this tube. But as this light appears to be coming from the focus of this lens called convex lens, so if it is if it consists, actually it is forming an image. Actually, when light rays are coming here, this will form a here this will form, whatever the light is coming from here, it forms an image here. They can say this is supposed to be formed the image over here. Okay, but this you can say that acts as a virtual object for this is a virtual image for it. Okay, and this acts as virtual object for this you will get an image over here, and this image will act as object for this lens, and hence after light passing through this, you get an image after passing through this. But here, not completely reflection elements we are having. Of course, we are using one lens here, refracting element. So of course, with the help of this, we will reduce these errors to maximum extent. even though we are using the refracting lens here. So then we'll get the final image after passing through this lens. So this is briefly about reflecting telescope or Cassegrain telescope. Yes, Cassegrain telescope, right? I hope it is clear for you. And here also, just as I told you, the derivation part of this magnifications we will not discuss here. I can say is out of portion for you guys. So, but we need to remember that the same and similar kind of relations we have to use while doing the numericals related to Cassegrain telescopes. For finding the magnification related to what you call magnification related to, well, what is that, least or you can say relaxed position, and magnification related to when the final image is forming at least distance of distinct vision and this. Okay, next next we'll see next one more numerical. You see here, yes, question number 80. Yes, here it is given that here it is given about the Galilean telescope. Now whatever point I have told you that you have to make use here. In Galilean telescope we use one lens as a convex lens, another lens as a concave lens. So next question number 80, same page. It is given that, listen the question carefully everyone. It is given that a Galilean telescope measures 9 centimeter. A Galilean telescope measures 9 centimeter from the objective to eyepiece. From the objective to eyepiece. What is that? It is nothing but length of the telescope. It is nothing but uh, f naught plus fe, f naught plus fe or ue, either anything you can take. F naught plus ue or fe is equal to 9 centimeters. And the focal length of objective fo is equal to 15 centimeters. Then its magnifying power is, what should be its magnifying power? So when you consider this is fe, that means ue you are taking it as fe means you have to consider what do you call, image is forming at infinity at relaxed position. That is the meaning of it. So that means the corresponding magnification I have to take it as m infinity is equal to what? Here we know that m infinity is equal to f naught by fe. F naught is given, then what is fe? Fe is not given, but f naught plus fe is given. How can you find fe for the to find this? Okay, let us consider this is equation 1. To find this, as we know f naught, let us try to find fe. To find fe, let us use this relations. F naught is this thing, but here, this is a Galilean telescope. Here itself you can take this carefully. For Galilean telescope fe will be negative. Fe will be negative. So this you can write it as, this implies, I can take this as 1, this is 2. So 1 implies f naught with sign convention. If you substitute the values with sign convention, f naught will be plus 15 and fe will be minus fe is equal to 9. So from this, on simplifying this, you can get if you bring it here it becomes plus fe, it brings here this side it becomes 19 minus 15 minus 9. So fe is equal to 15 minus 9 is 11 centimeters. 11 centimeters. This is fe. Once you know f naught and fe, directly you can find out this. What is that then? M infinity 2 implies m infinity is equal to f naught by fe. F naught is 15 and fe will be, what is this? Fe will be, is it f naught? So fe is equal to 15 minus 9, right? 11. Yes, is it 11? Oh, one second guys. Sorry, 1 second. Usually its magnifying power is, in this case even though here you have to just take the relation little differently guys. So what will you get here? Fe is 11, this will be 15 15 minus 9. What is it? Is actually 6, right? Yes. No, Rishwan. Very good, Nana. 6 it is, not 11. Very small mistake. It is not 11, it is 6. It is 6 centimeters. Right? So it will be 15 by Fe should be 6. Then what this should be equal to? 15 by 6 is 3, 5, 3 twos. So it will be 5 by 2. Say, what is this? Magnification. No unit for this. 5 by 2. That's it. If you see the options, it can be, it is not 2 by 5 or 5 by 3. 2, 5 by 2. 5 by 2 can also be expressed as 2.5. So this will be the magnification. So the calculations try to do little carefully, guys. Okay. uh, I got Fe is minus 6. Fe is minus 6. Actually, here no need to worry about the sign, guys. So here, of course, you can take it as minus, but magnification means only the value if you consider, you'll get this one. Okay, right. Fe can be 6 or minus 6 because I said right already. Here, if you consider Fe and then if you simplify, then you will get minus. Here itself, if you substitute with sign convention minus Fe, then you will get 6. That is the meaning of it. Okay. Yes. This is question number 80 and question number 81. Let us see question number 81. Is that point clear, Dinakara? Actually, minus 6, you can understand in that way. Usually, if you are not substituting the sign convention here, then you will get minus. Obviously, it will be a concave lens, so it will be minus. But here we have substituted as minus. Right, next question number 81. It is given that uh, a small telescope has an objective lens of focal length. An objective lens of focal length FO is equal to 140 centimeters. And an eyepiece of focal length 5 centimeters. Eyepiece of focal length 5 centimeters. The telescope is used to view 100-meter tall tower 3 kilometer away. The height of the image, the height of the the height of the image of the tower formed by the objective lens is formed by the objective lens. In the telescope, if you have the objective, if there is an object whose height is, it is mentioned that height of the object, a telescope is used to view 100-meter height tall tower, 100-meter height tower. This we will take it as the height of the object, which is 3 kilometer away. We can call this as the distance of object from the lens. Is 3 kilometer or 3 kilometers. 1 kilometer equal to 1000 meters. You can take it as all units should also, you have to take carefully, guys. It should be 3000 meters. And the height of the image of the tower formed by objective lens is what you are asked to find. We are asked to find what height of the image is what. Okay, so you have to remember that if this is an object of object height, and it is light is passing through this, when it is at a distance of UE, which is equal to UO, object distance equal to 3 kilometers, then an image is formed here. Then an image is formed here. Okay, and this the height of the image of the tower formed by object. So what is the height of this image is the question. Height of the image is the question. We know that if you know magnification, m is equal to angle subtended. I can say, you can take it as beta by alpha, but angle subtended by image by angle subtended by alpha, angle subtended by object. That is one way. The other way, only for a single lens, if you consider magnification, it is equal to magnification is equal to what? You can consider here. Yeah, if you say this is object height by object distance, in this case, if you take alpha, this is alpha. Yeah, and if you consider this is image, this is image, and this is subtending an angle. Actually, it is supposed to be same. It is supposed to be same. This can be expressed as, but this distance will be different. Okay, so you can say this is equal to. Okay, how can you express this? This is equal to what you will get here to find this. Yeah, you can take it as a HO. Let us consider this angle is HO by this angle alpha will be HO by UO, and this will be not we are not this directly considering the magnification. The angle, if you say, the angle will be this angle and this angle if they are equal, and this will be equal to HI by image distance. Image distance can be taken as the focal length of objective in this case. Okay, so from this we can say height of the image is equal to HO by U naught into F naught. So it is equal to H naught is height of the object is given as 100. Distance of the object from the lens is 3000 meters. Is 100 meters is 3000 meters. So even though these are in meters, meter can cancel, then no problem. But F naught is given in centimeters. So different units we are using. So final value we get in centimeters only, guys. That you have to be little careful. HI will be equal to F naught will be 140 centimeters. So this meters gets cancelled. Final answer will be in centimeters. Final answer will be in centimeters. Now these two zeros, 1 0, 3 zeros will cancel. 14 by 3 you will get. So option, and therefore HI will be equal to 14 by 3 centimeters. So option 1 will be the correct one. This is how we have to work it out, guys. Right? Next. Similarly, question number 82. Question number 82, we can just let us do this and let me wind up this. Question number 82. Question number 82. So here I said some that 1 by u value you have used directly, right? Here you have to make use of that. So let us try to understand how can you work it out. So the magnification produced by an astronomical telescope for normal adjustment is 10. Normal adjustment means relaxed position. The normal adjustment, that is m infinity, is nothing but f naught by fe is equal to what? 10. And the length of the telescope is 1.1 meter. Length of the telescope is nothing but what? F naught plus Fe is equal to, you can take it as how much? 1.1 meters. 1.1 meters. The magnification when the image is formed at half distance of distinct vision. Magnification at a least distance of distinct vision is what is that? F naught by Fe into 1 plus Fe by D. But half of this means this will be half. This we have to take little carefully. That's it, guys. That's it. So now instead of using this, you can also take this expression as how can you take this is how can you take this is actually we know magnification is nothing but f naught by ue, right? F naught by ue, f naught by ue. But by using lens equations, if you go back here in the lens equations, somewhere here it is in white, yeah, here I put this in the box, right? 1 by ue, 1 by ue is equal to 1 by fe plus 1 by d. This expression you can use. 1 by ue is equal to 1 by Fe plus 1 by D. So 1 by UE. This if you want to make use, then you can write it as F naught into 1 by Fe plus 1 by D. Here F naught by Fe is given, F naught plus Fe is given. If you know F naught and Fe, then you can do it, right? But directly they have not given, then how can you make them how can you make use of this? D anyway is, of course, here that D is nothing but D by 2. Here you have to take this as D by 2. So what is F naught and what is Fe? From this you can say F naught by Fe is 10 Fe. So let us say this is 1, this is 2. Let us take the next step from 1. 1 implies F naught can be expressed as 10 Fe. Can we take F naught can be expressed as 10 Fe? Okay. And anything else is given here? That's it. If it is 10 Fe, then equation 2 implies F naught plus Fe is 1.1. So F naught, if we take it as 10 Fe, 10 Fe plus Fe is equal to 1.1. Right? From this it is 11 Fe. You can say 11 Fe is equal to 1.1, or Fe is equal to 1.1 by 11. Fe is equal to 1.1 by 11 meters. It is given in meters, guys. This is given in meters. On simplifying this, we multiply with both numerator and denominator with 10 by 10, you will get 11 by 110, or Fe is equal to what? 1 by 10. So it is equal to 0.1 meters. Fe is 0.1 meters. Careful about the unit. Fe is 0.1 meters. Once you know Fe, now we can find out F naught. F naught is 10 Fe, right? So here, so let me do it here. Yep. Let me do it here. So as F naught, this implies F naught is equal to 10 Fe. It is equal to 10 into Fe is 0.1. So it is nothing but how much? 10 into 0.1 only. So it is 1 centimeter. Sorry, 1 meter. It is in meters, right? It is 1 meter. 1 meter can be expressed as, if you see these values here, d you have to take in centimeters, means you have to take this also in centimeters. Then this is 1 meter. So f naught is equal to 1 meter, or it is equal to 100 centimeters, and fe is equal to 0.1 meter. If you want in centimeters, so can you write this 1 meter equal to 100 centimeters, right? So it should be 10 centimeters, because here we are going to use d in centimeters only. Okay, that's why. So then, as d is equal to 25 centimeters, d by 2 will be 25 by 2. By substituting all this here, you can take this as, already have taken equations 1 2. Let us take this as equation 3. Substituting this in 3, you will get magnification at d by 2. So now 3 implies magnification at d by 2 is equal to, what is that? F naught into 1 by Fe plus d by 2. It is equal to F naught into 1 by Fe plus 1 by d by 2. So you can also write it as F naught into 1 by Fe plus 2 by d. 2 by d. And substituting these values, you can get F naught is F naught 100, Fe 10. Yeah. F naught 100 into 1 by 10 plus 2 by 25, all are in centimeters. And simplifying this, 25 plus 20, 45. 100 into 45 divided by 10 into 25. 10 into 25. So 1 0 gets cancelled. Then 5 5s, 5 9s. Got it? Yes. Then 5 ones, 5 twos. So 9 into 2, 18. So what you will get? Magnification at d by 2 will be equal to 18. Got it? This is how you can work out this kind of questions. Got it? It is 18. It is 18. So likewise, you guys try to work out the questions from level 1 also. Level 1 and level 2 exercise 1 and level 1 exercises 1 and 2 exercises. Try to finish these questions by yourself, guys. In the next session, we'll go ahead with this. The telescopes part also completed, and resolving power of telescope and all will not be there here, guys. We'll discuss that particular part in what you call wave optics. Wave optics at the end we'll discuss. Not here. Resolving power of telescope part we'll discuss in wave optics. So in the next session, we'll start with wave optics, specifically interference of waves, Huygens-wave theory, interference of waves. And if possible, we'll try to discuss about a YDS, Young's double slit experiment. Otherwise, we'll try to discuss interference and some numericals based on that. YDS you can discuss unsolid. If possible, try to discuss tomorrow itself to some extent. Okay. Okay then. As the time up, I am winding the session. Okay, guys. Take care then, everyone. Bye bye.